Hi Southwoods, Mrs. Lindsay here to talk about geometric sequences. A sequence, if you recall, is a progression of numbers. Now, in our first example, we have what's called an arithmetic sequence. So the first four numbers, 1, 3, 5, 7, progress by adding the same amount to get to the next number. So I take 1 and I add 2, I get to 3. I take 2, I add 2, I get to 5, and so on. I add 2, I get to 7. This is a constant rate of change. To find the next three numbers in the sequence, those were the first four. So if I want to find a sub 5, a sub 6, and a sub 7, I would simply add 2. So I would add 2, I'd get 9. Add 2 to that, I'd get 11. Add 2 to that, I would get 13. So this is an arithmetic sequence. It's got a constant rate of change. It looks very much like a linear function. It's discrete, so it's not connected, but if I was to connect them and put arrows, it would look just like a linear function. So what is the rule? Well, I started with 1, and I added 2. If you remember the recursive form, we have to say what we start with. So a sub 1 is 1. And then to get to a sub n, I take my previous term, a sub 1, and I add 2. That would be the recursive form. The next sequence, I also start with 1, but here clearly we're not adding to get to the next term, we're multiplying. And we're multiplying by 3. So this is not constant, and it does not behave like a linear function. So if I have my first four terms here, 1, 3, 9, 27, to get to my next three terms, a sub 5, a sub 6, and a sub 7, I would have to multiply by 3, giving me 27 times 3, 81, 81 times 3, 243, and 243 times 3, 29. Again, the rule is we started with 1, but we multiplied by 3. To write the recursive form, again, you have to tell me what your first term is, and again, that's 1. But to get to my nth term, I'm going to multiply 3 times the previous term, a sub n minus 1. Now, as you remember, recursive form had its benefits, but we had a hard time if we needed to get to a term number that was very far down the line. So what were the difference between these two? The arithmetic sequence was a constant rate of change. It behaved very similar to a linear function. As a matter of fact, it was just the linear function in discrete form, just separate dots. If I connected the dots, it would look just like a line. When I multiplied, we did not have that constant rate of change. That was called the geometric sequence. And it behaved very much like an exponential function. So, if we have this sequence down below, 2, 6, 18, 54, this is not a constant rate of change. We're not adding the same number to get to the next term, but we're multiplying. So to get from the first term 2 to the next term, we have to multiply by 3. That'll give 6. to get to the next term after that, instead of calling it 6, let's leave it as 2 times 3. We have to multiply by 3 again. That'll give us 18. In order to get to the fourth term, 54, we're going to take 2 times 3 times 3, which we know is 18, multiply it by 3 again, and that'll give us 54. If you notice, we're multiplying these terms by one less ratio, or one less 3, than the term number. So to get to the fourth term, I'm taking 2 and multiplying the ratio 3 times. So to get to a sub n, I'm going to take the first term, 2, multiply by the common ratio, but it's going to be one less time than the term number. So this, fortunately for you, is going to be given to you on your reference sheet. To get to the nth term, you take the first term, multiply it by the ratio one less time, n minus 1. So you're going to raise it to the n minus 1 power. All right, let's see how that works. Here's what you need. A sub n, which is the term we want, we would need the term, and we would need r, the common ratio. Basically, the common ratio is what you're multiplying to get to the next term each time. And I would have to tell you which term number I want. So, if I want a geometric sequence that starts with 90, and the common ratio is negative 1/3, then I can now write in what we know. We know a sub n. We know a sub 1, the first term. That's 90. We know the common ratio. That's what we're multiplying each time, negative 1/3. So if we start with 90, there's our a sub 1, our first term. We multiply by negative 1/3, we get negative 30. When we multiply again by negative 1/3, we get 10. We multiply again by negative 1/3, we get negative 10 over 3. And if we multiply a fifth time by negative 1/3, we get 10 over 9. Notice how when you're multiplying by a negative common ratio, our terms jump back and forth between positive and negative. Okay? But now if I wanted to get to the 10th term, instead of counting each time, I might want to use the formula that was given to us on our reference sheet. A sub n equals a sub 1 times r to the n minus 1 power. And you can do this all on your calculator. I've written it out for you. But basically, to get to a sub 10, the 10th term, we multiply by the first term, a sub 1, which is 90, times the common ratio, which is negative 1/3, and raise it to the 9th power, which is 1 less than the term number. Do the calculator, I get approximately negative 0.00457, but I took the liberty of math fracking that. And if you want the exact answer for a sub 10, that would be negative 10 over 2,187. And that would be your 10th term. All can be done right there on the calculator. Now, you can solve problems, word problems like this as well. We have Anne, who jumps off a bridge above water. Fortunately, she has a bungee cord attached to her. And that bungee cord stretches 120 feet on the first jump. So clearly here, that's my a sub 1, or my first term. Now, each bounce stretches the chord only 60% of the previous bounce in height. So my common ratio is 60%, which I need to turn into a decimal, 0.6. Okay? Now, I can use the table here, which I did. And if I want to multiply each term by 0.6, the second term I get 72. The third term, if you look on the